Hi everyone. Just addressing your feedback from today about today's discussion on the Nernst equation. First question here is, I still don't understand the relationship between the Nernst equation and the free energy equation. So I'm not entirely certain which free energy equation you're referring to, but in the context of the Nernst equation, I think you're referring to this expression, which is a way of calculating delta G under non-standard conditions versus G at standard conditions, which is given by this expression. And then the Nernst equation is this. And again, the Nernst equation similarly is a way of calculating the cell potential at non-standard conditions given what it is at standard conditions. So this ends up being equal to negative RT over NF natural log of Q. So how do you get how are they related? Essentially, they are the same equation. They're expressing the same ideas. How does one particular potential or free energy difference change from its standard conditions as you adjust the conditions, as you change concentrations or change pressures? So the way I think about this is, here is your standard conditions. And to some extent, you can think about this. All of these terms here, you're essentially just subtracting off one big term, and all of these terms together, they represent, in the way I see it, is sort of a correction factor to the cell potential. If things were at standard conditions, this is what the cell potential would be. If you change those conditions, then essentially you're adjusting the actual cell potential. You're either subtracting a little bit or you're adding a little bit. And so again, I think of this as a correction factor. That's the term for some reason I want to use to describe it. It's some correction factor that corrects for consideration of non-standard conditions to figure out what is the cell potential or what is the free energy change under those non-standard conditions. And again, I'll assert that they are essentially the same equation because of how delta G and the cell potential are related. Delta G is related to the cell potential by let me make this just a little bit easier to read here. So I should have that delta G is equal to negative NF E cell, and this relationship is about how you can connect this equation to this equation. So again, just to reiterate, they are essentially the same equation. How would you put the Nernst equation into words? I think of the Nernst equation as a way of calculating cell potentials under any conditions. The idea is you might know what it is under standard conditions, and those you can calculate with standard reduction potentials, because standard reduction potentials are also given at standard conditions. If you're under non-standard conditions, that's when you adjust the standard cell potential. You adjust it by taking into account all those other non-standard conditions. So that's a lot of words to describe it. But yeah, basically, Nernst equation describes the cell potential by accounting for or correcting for non-standard conditions. We can calculate standard cell potentials by just calculating the difference in reduction potentials. We've done a handful of examples with that. But again, those are standard reduction potentials. And the Nernst equation allows you to calculate cell potentials under any set of conditions, just in the same way that we were able to calculate delta G under certain non-standard conditions. And again, those non-standard conditions here are represented by the reaction quotient, which should still be the concentration of products over reactants. So whatever those concentrations or partial pressures might be, they don't have to be 1 atmosphere, 1 molar. And the temperature is no longer required to be 298 Kelvin, 25 degrees Celsius. We can do this at different temperatures and also calculate the cell potential. In the question we worked through today, wouldn't changing the mass of the iron, the metal, the solid iron, wouldn't that change its concentration and then in turn influence the reaction according to Le Chatelier's principle? I'll assert that it won't change, it won't shift the reaction, because if you have a piece of metal, so I got one of these metallic balls here, and if I were to cut in, here's an example. We think of concentration, molarity, as being equal to the number of moles of a substance over the volume that substance is distributed through. So it could be the moles of a solute in the volume of a solution, or you could talk about the molar concentration of a metal. How many moles of atoms are there in this magnet over the volume of the magnet? But if I were to here, let me give you the analogy that I want to make here versus an analogy here with density. Density would be similar relationship. It's an intensive property, just like concentration is. If I cut this ball in half, its mass would decrease, but so would its volume. And the same basic idea here is that if I had some metal iron bar and I cut it in half, so I only had half as much mass as I did before, okay, its mass is reduced by a factor of a half, but so is its volume. That volume there is also being decreased. And if I cut the ball in half, just because I've changed the mass of what I'm about the half of the ball that I'm looking at, I haven't changed the density of the material, nor have I changed its concentration. I decreased the number of moles by a factor of a half if I cut this in half. But I would also decrease the volume by a factor of a half. And so as a result, the concentration isn't changed. And so that's a big point that I've tried to emphasize a few times as one of the key reasons why we don't include, or we don't need to include, solids and liquids in the law of mass action is that their concentrations are fixed. You can't really compress them, you can't change their volume without changing the mass, and you can't change the mass without also changing the volume easily. So no, you would not have to consider that in terms of Le Chatelier's principle for the reaction we discussed. Okay, when it says following non-standard conditions, does that mean that any conditions which aren't listed, should we assume those to be standard? So like today in class, I gave an example problem where I had a reaction that depended upon 3 parameters. It had the concentration of iron, the concentration of hydrogen ions, and the concentration of, or rather the partial pressure of gas. And I only listed under non-standard condition the concentrations of the 2 solutes in solution. And then we assumed that the partial pressure of hydrogen was still 1 atmosphere. So your question is that what we should always assume? Technically, no. Just because you're not told what it is, you shouldn't necessarily assume that it's standard conditions. But in the context of a simple problem like this, yeah, I think it's fine to make that assumption. Obviously, if you're not given any other information to go with, it's a reasonable assumption. Just like if I don't say the temperature, like in that whole discussion, I don't think I said the explicit temperature, so it's safe to assume that it's being done at standard temperature, which for us, or the temperature for standard conditions would be 298 Kelvin. So we can make that assumption. And I would say generally it is safe to assume that if I don't tell you what one of the non-standard conditions is, you can assume that it's standard. In real life, in a real problem, no, you shouldn't necessarily make that assumption, but sometimes you might have to. So that's what I would say. Is there a situation where you couldn't use Le Chatelier's principle and you would have to use the Nernst equation? And would you specify that on an exam? So yeah, like today, we tried answering the question in 2 ways. One, just by looking at how the equilibrium, how the reaction quotient would have been affected by changing the conditions, changing concentrations, and we were able to predict how the cell potential would change just using Le Chatelier's principle. When would you need to use the Nernst equation? The only time I would say you really need to use the Nernst equation is if you want to explicitly calculate what the cell potential was. So would I specify that on an exam? Yes, I will say calculate the cell potential, in which case you have to use the Nernst equation. If I just want you to predict whether the cell potential increases or decreases, I would say, does the cell potential increase or decrease? And that you could answer either by Le Chatelier's principle or by understanding the functional form of the Nernst equation, which is, I would say, more difficult than actually doing an exact calculation. Logicking to yourself, okay, if I have this, so I have concentration of products over concentration of reactants, I have to recognize, okay, if I increase the concentration of the products, then I'm increasing the magnitude of this correction factor. So this whole, if I increase the concentration of products, the entire correction factor increases in magnitude. But then I'm subtracting off this concentration factor, so I expect the cell potential to decrease. So that actually, in my opinion, is a little bit trickier than just noting, well, if I increase the concentration of the products, the reaction should shift backwards towards the reactants, meaning that the forward reaction is becoming less favorable. And if the forward reaction is becoming less favorable, then I expect the cell potential to decrease. So they're both valid ways of answering it, but I would say you only need to explicitly use the Nernst equation if I ask you to calculate something. That's when you absolutely have to use the Nernst equation. When you directly connect the equilibrium constant with cell potential, would that involve a problem that also has changes in concentrations, like in question 3E from the worksheet? I would say, generally speaking, no. This relationship that I presented to connect the equilibrium constant with the cell potential, so I said the cell potential under standard conditions should be RT over NF natural log of the equilibrium constant. That is specifically trying to relate standard cell conditions to what those conditions would be, or what the concentrations would be at equilibrium. If you're looking at changes in concentration, that's when you need to use the Nernst equation. And now, that being said, the Nernst equation is also related to the equilibrium constant in the same way that the equilibrium constant is related to this equation. These two are related because we've just said, okay, we just said that the cell potential is related to the equilibrium constant. If I'm doing things at non-standard conditions, that's when I utilize the Nernst equation, and then the cell potential here, I can basically insert this whole expression there, and then I can relate the cell potential under non-standard conditions to an equilibrium constant if I wanted to. So I would say it's possible, I just don't think I would ever ask a question like that. Let me see here. Is the final going to have an even distribution of what was covered on each midterm? Is there, and as well, is it going to be evenly distributed with new material? I haven't written the final yet, so I don't want to definitively say one way or another what the distribution is. It will have we have some new material, not that much new material, but we have new material on electrochemistry to assess. So I will certainly have some questions on electrochemistry. And then beyond that, I would say everything else is going to be about evenly distributed between discussions of acid-base equilibrium, solubility equilibria, thermodynamics, and kinetics. I'm going to think of, there is a whole dedicated chapter to equilibrium, just chemical equilibrium. But I'm of the opinion that you can think of acid-base reactions, acid-base equilibria, buffers, and solubility equilibrium. Those are all applications. They are all specific cases of chemical equilibrium. So I may not have a whole section of the test, dedicated to chemical equilibrium and just plain straightforward chemical equilibrium, but I may still be implicitly testing on it by testing people on acid-base equilibria or solubility equilibria. But I guess to answer your question, yeah, things are going to be basically evenly distributed for the entire course. So it won't be, half of it is not going to be new material. I would say I'd roughly estimate maybe a fifth of it would be new material and the rest will be old material. Again, please do not quote me on that. That's just my personal estimate of how I plan on weighting things at the moment. And last question I got here was units of C. What were these units? So this is in relation to something I wrote up here earlier, which was, what are the units for C? So the units in this equation here are, this N here represents moles. It's the number of moles of electrons, though, specifically. So if I were going to write the units here, my units are moles of electrons. The Faraday constant has units of coulombs per mole. So C here, that is the unit of coulomb, which is the SI unit of charge. An electron, for instance, an individual electron has a unit charge, which we call Q, and that unit charge is 1.6 times 10 to the negative 19 coulombs. This is our standard SI unit for charge. Faraday's constant is the charge, the number of coulombs of 1 mole of electrons. So the moles of the electrons, those should end up canceling each other here in this calculation. And then the cell potential has units of volts. So you might look at this and say, well, how am I supposed to get units of energy here? Because delta G, that's a free energy. It should have units of energy. Because it doesn't look like those are going to cancel. I get coulombs times volts. And you're right, you don't just immediately get volts from, you don't immediately get joules from coulombs times volts, but what I will remind you is that the volt itself is a derived unit. 1 volt is defined as 1 joule per 1 coulomb. It's how much energy you pick up by passing a coulomb of charge through this voltage drop. So with that in hand, this here then has units of joules per coulomb, and then all of my units cancel out, and I'm left with units of joules for free energy, which is what I expect. There's somewhat implicitly there, I admit, this is an implicit point, is that the reaction usually is written as a mole of the reaction, so we can sort of hand-wavingly insert a joules per mole. Like for the calculation I got today, I believe the calculated value I had was minus 84,480 joules. That was for 1 count, 1 mole of this reaction going to completion. That mole of the reaction had 2 moles of electrons being transferred, but the reaction overall released 84,000 joules. So we'll talk about the amount of energy you get out per mole of reaction. I know that's a little awkward, but mole of iron atoms, there's 1 iron atom that's reacting in that balanced chemical equation. Okay, so that's all the feedback questions for today. If people have subsequent questions, please shoot me an email. I'd be happy to address them. Otherwise, take care and have a good weekend, everybody.